design engineers.
My name is Jose Arguedo Pobran, and I'm a design and manufacturing engineer.
My name is Riker Minell. I'm a financial analyst and a design engineer.
And we would like to thank Newick for being our sponsor during this, and our mentor, Dylan Fontaine, who unfortunately was not able to make it today. So for those of you who don't know exactly what implosions are, an implosion is the process in which an object is destroyed by collapsing in on itself. They are triggered by a pressure difference between the inside of the implodable and the outside environment. This is done through what's called the buckling pressure, and this can be calculated using what's called a critical collapse pressure equation and von Mises stress. Practical applications for implosions are pretty limited, but our application specifically is for submarines that fail while underneath water. Our system can launch an emergency signal to the surface, and the implosion can be manufactured to implode when a certain depth is reached underwater. So say a submarine were to fail and fall below its traveling depth, the system would activate on its own. An example of a submarine doing just exactly this is the Kursk Russian submarine, which happened pretty recently in the year 2000. It had what is believed to be a faulty weld in a torpedo, which caused a hydrogen leak, and while it was underwater, and then caused an explosion. The Russian Navy failed to realize that this ship had sunk, and rescue initiatives didn't even take place for about 6 hours. And during these 6 hours, there were still people alive in the ship. Next slide, please. So for our project, we had to expel a payload underwater using an implosion or explosion. We use implosion simply because it's based on pressure, and pressure increases the farther down you go underwater. The system cannot use any power source whatsoever, so it's strictly mechanical only. The payload must be neutrally buoyant, and the system does not necessarily need to be reusable, but it would be better if it was. The project included size constraints. Outer tube was the base of these constraints, with the diameter being some number that we could choose, and we call this D. The length of that 10 times that diameter. The payload needed to be 3/4 that diameter, and the length had to be 2 times that diameter. The pressure we could decide on, and we chose the pressure that the implodable would implode at, we could decide on, and we chose about the average depth range that a submarine would travel at about 286 feet, which corresponded to a pressure of 127 psi. The life cycle of our system is about 3 to 5 years, and the cost is well below our budget of $600.
So here we have the financial analysis for the project. The greatest cost for the design was simply the time that had to go into making it. In a real world scenario, it would have cost about $16,640 in labor to design and fabricate the first prototype. Every additional unit would cost about $300 in parts and about $100 in labor to recreate using the current manufacturing process. However, as the prototype does not have the capability to utilize an implodable trigger like the full design does, it is unlikely that it would need to be mass produced. To manufacture the full design, it would likely add about $40 to the cost in parts, and would increase. It would take increased labor to assemble as well due to the increased size. So the created prototype only required a purchase of $121.93, meaning that the group only had to utilize about 20% of the total budget for the project.
So for our initial design approach, you can see on the right that our full model with the outer tube housing all of the internal components. And on the left, you can see the full model with a see-through, on the right, a see-through outer tube to view all of the internal components. So our initial design features a 5-foot-long, 6-inch diameter outer tube made of PVC. It houses and expels a neutrally buoyant payload that is 1 foot long and has a 4.5-inch diameter. The payload features two caps that were 3D printed and is filled with material to equal out the mass related to the volume of water that it displaces, which would make it neutrally buoyant in water. The trigger is a 1 foot long, 2.5 inch diameter aluminum pipe, which has a critical buckling pressure of 100 psi, which would equate to a maximum allowable depth underwater of 286 feet. The payload rests on a 3D printed platform that is attached by screw hooks to 4 springs in tension with a maximum spring force of approximately 14 pounds. These springs are also attached to a 3D printed insert part that sits at the top of the outer tube. And on the other side of the springs and the platform are 2 connecting rods made of aluminum that are threaded onto the screw hooks in the platform. And since we have such a big length in our outer tube, these connecting rods extend about 40 inches, where they are guided by PVC pipes with matching insert holes for 2 pins to oppose the spring force when loaded. And these 2 pins are attached to a steel strapping like collar that sits around the exterior of the implodable cylinder. And when the depth of 286 feet is reached, the implodable cylinder will collapse in mode 2 inwards, pulling the pins out of the connecting rod and guide holes, thus allowing the full spring force to pull upwards on the platform and the payload. For our prototype, we decided that it was best to test the top mechanical half of the design separately from the implodable cylinder trigger, as we had enough data from testing in the DPML lab, and that ensured the functionality of this cylinder. So this meant that we were able to reduce the length of our outer tube to 2 feet, as we didn't need to have the implodable cylinder at the bottom of the outer tube and all the extra length in those components. So the diameter of the outer tube in our prototype stayed the same at 6 inches, and the payload length and diameter was also unchanged from the initial design. We also added nuts and bolts to pass through the connecting rod guides and outer tube to secure the 2 to each other, as well as to provide a poka-yoke feature that would stop the connecting rod at the exact length where the holes for the pins would line up perfectly, allowing for easier pin insertion and preventing the risk of overextending the springs. And that can be seen on the bottom right picture, the nuts and bolts. And for this prototype and in the testing, we manually pulled the pins to release the spring force to simulate the collapse of the implodable cylinder, since we weren't going to be able to actually use the implodable cylinder in our testing. Go back one.
All right, so now moving on to the testing, we were lucky enough.
Let's skip one there.
Oh, sorry, no problem.
So from our initial design to our prototype, there were a few components that were redesigned that ensured the success of our prototype testing. For the payload, we used silicone to seal the PVC and both the end caps, as well as used a mix of lead balls and water on the interior to achieve pretty much neutral buoyancy. It was just a little bit off, but that resulted in the payload being able to float freely with a slight tendency to slowly sink. From our initial design to building our prototype, we realized that the original connecting rods that had a diameter of 0.4375 inches was too loose of a fit. So we ended up increasing this diameter to 0.5 inches, which ended up fitting perfectly. We then tapped and threaded the top of these rods to screw into the screw hooks that are connected to the platform. As mentioned previously, the only other change in the design was the addition of the nuts and bolts on the bottom of the connecting rod guide into the bottom of the outer tube to give the perfect fitment of pinhole alignment, as well as for the prevention of the overextension of the springs. The rest of our final design was unchanged, and the final design was kept at 5 feet as the design specifications required, as opposed to the 2 foot length of the prototype with the manually simulated implodable trigger.
All right, and now moving on to the testing slide. So the first half of our project was tested in the Tuatel Aquatic Center here at URI. Shout out to them for letting us use their facilities. So our payload was tested in the pool and it proved to be slightly negatively buoyant. For our application, that wasn't a problem. We just needed it to float on its own and not move drastically. So that was accomplished. The, the payload was held inside the outer tube and tested multiple trials. Um, every trial went successfully, and if we could show the video of our setup, how we did the trials. So that's me holding the outer tube, Ryan's under pulling the pins, and as you can see, the outer tube is expelled from the payload is expelled from the outer tube, and when it loses its energy, all the velocity is lost. It just floats right under the surface of the water. So the payload and the expulsion mechanism both proved reliable after multiple tests. Moving on to the next slide, and talk about the testing that went on in the DPML. All right, so the Dynamics Photomechanics Laboratory was very helpful during this project. We used their facility to run the tests on the implodable. So actually, one of the grad students, Irene, that I worked with, she provided all the data that we used in terms of the implodable. So she's been running tests on aluminum cylinders for a while now. She knows, she's very knowledgeable in what she's doing, and she gave us the data for her most recent test on very similar aluminum tubes than to the ones that we decided to use for our implodable trigger. Her tubes were 12 inches in length with an outer diameter of 2.5 inches. They had a wall thickness of 0.049 inches, and after her tests were run, she got an average critical buckling pressure of 229 psi. So the way that they test the implodables in the DPML is, as you can see on the left side of this slide, this is the diagram of the big tank that they use in the DPML. So this is a very large tank that can be filled up with water and pressurized through the top. They pump nitrogen gas into the tank, and that pushes on the water and pressurizes it to their needed value. They also have these little portholes that allow these Shimanzu high-speed cameras to record the implosion itself. As you can see in this diagram, the tube has some speckling, so it's literally just black dots facing the cameras. So what that is for is so that the cameras can pick up the speckles and later be transferred into a 3D digital image correlation software. And what that software does is it captures the dots and watches them as the tube implodes, and it compares the positions of these dots to give you strain data, the strain that is being felt by the implodable. And these cameras can run up to very, very high frame rates, so you can see the implodable collapse in on itself in slow motion, and it was very cool. I was trying to get a video for you guys, but unfortunately I would need to have the software to run that video on my computer, and I do not. But the implodable collapses and the inner walls touch, and as you can see, they have some transducers on the outside of the tube to get those shock wave data. So what we did is, with all this data from the DPML, we were able to decide what size implodable we would need, and we went with a similar sized implodable. Our aluminum cylinder was 12 inches long as well, and had an outer diameter of 2.5 inches. The only difference was the wall thickness. We lowered the wall thickness to 0.035 inches, and we're able to use the critical collapse pressure calculations, von Mises calculations, and Abacus 3D modeling to support our buckling pressure of 127 psi.
In conclusion, the testing of the prototype demonstrated that the expulsion method is effective and reliable. With the data we acquired from the DPML lab, we are confident that the implodable trigger is a reliable design for the full-scale concept. While the payload was not totally neutrally buoyant, the negative buoyancy actually proves that the success of the test demonstrated a very effective expulsion method. As for further work, the only further work we really could do would be to create a truly neutrally buoyant payload and a full design model. And those would be the next logical steps if we wanted to further test our design.
Okay, team, your time is up. Thank you for your presentation.
Thank you. Thank you for your